Assalamualaikum. Good morning, everybody. Well, this is chapter 2 of solid state physics, and we are discussing about Schrodinger equation. Some of you might pronounce it as Schrodinger equation. Some of you might pronounce it as Schrodinger equation. Doesn't matter, but this is the right way to write the name of Schrodinger. Its name, it was the name of a famous physicist named Erwin Schrodinger. And he's very famous of creating the equation of derivating the equation of Schrodinger equation. This is the gist, the gist or the starting point of the quantum chemical quantum physics study. So let us take a look. What does it mean by the Schrodinger equation? Why Schrodinger equation is very important for physicists or material technologists to understand materials in this world. Today, we are looking at the most fundamental equations in all quantum mechanics, the Schrodinger equation. Now, I know that, I know what you are thinking. The quantum mechanics sounds intimidating, right? But here's the thing. By the end of this course, you are going to understand not just the math, but what it actually means physically. So we'll use interactive simulations, animations, and real examples from materials science that directly connect to your future work in material technology. So let's get started. So here are the things that we are going to accomplish today. First, you will understand what a wave function is. A wave function is an equation, series of equations that tells us everything about the movement of subatomic particles, for example, proton, electron, and neutrons. So you need to understand what a wave function is and why we use it instead of classical trajectories, why we use quantum mechanics instead of classical physics. And second, you will learn to derive and apply the time-dependent Schrodinger equation. Yes, time-dependent Schrodinger equation. Time-dependent means we could predict what will happen at certain time or what has happened at certain time before. We could predict what will happen and what has happened to a certain particles, proton, electron, neutron, using Schrodinger equation. There is one famous professor in physics sorry, I can't remember the university name, but his name was Daniel something. Daniel something. He's Jewish, and he used the Schrodinger equation to predict who will win in the next election of certain countries. And he has simulated Malaysia, of course, and he shared his view on Malaysia, but I cannot reveal it. All right, anyway. And yes, we will do the full derivation step by step, the Schrodinger equation. And third one, we will separate variables to get the time-independent version. The first version is the time-dependent, and we will learn the time-independent version of Schrodinger equation. What does it mean by time-dependent and time-independent? Later, we will discuss about that. This is what you will use most often in materials calculation. We will use time independent in most of the time, right? These outcomes map directly to your program's learning goals, applying physics knowledge, solving problems, and developing new analytical approaches. And everything we cover will appear on your quizzes, tests, and final exams. So stay engaged, bear with me. Where is it? Okay, let's see the wave function. Okay, let us start with section 2.1, the wave function. This is where we make the jump from classical to quantum thinking. This is the paradigm shift from classic to quantum thinking. But I promise the simulation will make it clear. We'll use simulations. Look at these simulations, or more like animation. This is animation. Look at this animation on the right. So at the top right corner, you see a moving ball, bouncing ball. That's classical mechanics, because you could see the ball, the trajectory of the ball, and you could somehow predict where is the next location of the ball that will move, right? So notice how the ball is visible from your naked eye. It has a definite position. At every movement, it follows a clear trajectory. You can literally point and say the ball is right there. Okay? So now look at the bottom animation, bottom right hand side of the animation. So this is quantum mechanics. Notice something important. There is no visible ball, right? Instead, you see this wave pattern, which probability cloud. This is probability cloud. The probability of any subatomic particles, proton, electron, neutron, or we could say we focus on electron only. Don't care about the proton and neutron first. Let's say these are the probability of electron could exist in materials. This is the fundamental difference. In quantum mechanics, we cannot say the electrons is here because we cannot see from our naked eye, but we could predict using the Schrödinger equation or the wave function. We could predict the probability. The electron might be over here, or here, or here, or here. We could predict that using calculations. So we only can say there is a probability distribution showing where the electron might be found if we measure it or if we calculate it. Now click the start button and watch the animations run together. Okay. Anyway, I have clicked the start button anyway, right? Or you could always play around with the speed, the simulation speed. You could reduce and you could increase. How about if we decrease this? See the simulation slowly, or you could pause, right? So the probability cloud, the ball, this one, the bouncing ball, you could always see the ball, the moving ball, and the probability cloud over here. These are the probability cloud. The electron might be over here at certain time, or might not be there at certain time, right? Let's try to resume the simulation. Oops. Yeah, there you go. See the probability density, the real part. Because in wave function, there are real part, there are what do you call this? The imaginary part. So the real part in this simulation denoted by the dotted lines. Right. Sekejap, ada orang WhatsApp saya. Sekejap, saya nak WhatsApp. Alright. Before that, from here. The classical particles moves predictably. The quantum wave spreads and oscillates. The quantum wave, it spreads and it oscillates. This is wave particle duality in action. The graph, the right bottom graph is the wave-particle duality in action. We have the wave and we have the particle duality. For electrons in materials, we must use the quantum description. We can predict where the electron is located in materials using this Schrodinger equation. And what is exactly is this wave function? We call it as psi. The trident symbol. The trident symbol is a wave function. We call it as psi psi. The pronunciation is psi. The spelling is psi. So it's written as the Greek letter. It's a complex number. Wave function psi is a complex number, meaning it has both real part and imaginary part, shown in blue and green. So you have this graph on your left-hand side. We have blue and also green. The blue one is the imaginary part. In the imaginary part, the blue one, the dotted blue line is the imaginary part of the wave function, and the green solid line is the real part of the complex number. Right. Here's the key insight. Psi itself is not directly measurable. Psi is not directly measurable. It's an amplitude. Psi is an amplitude. Okay. But when you square its amplitude, you got psi squared. You will get the probability density. Psi is the wave function. You only get magnitude. But to measure the probability of the electron to exist, you need to do the psi square. Absolute psi square. You need to calculate the magnitude. No negative part, but only positive part. Psi square. This is how you calculate the probability density. That is measurable. The psi square is measurable. Psi is not measurable, but psi square is measurable. Now think of it like this. The wave function, the psi, is the mathematical object that encodes everything about the particle's quantum state. Everything is crammed together inside, right? So when you want to find where the particle is, you calculate the psi square. When you want to find its momentum or energy, you use mathematical operators on psi. So we have three things today. We have psi. Psi is a wave function that tells everything about the particle. It contains the real part and imaginary part. Then you want to know the probability of the electron to exist at certain places. So you need to do the psi square. Okay, absolute psi square. Then if you want to calculate the momentum or the energy of that electron, you need to use the mathematical operators on psi. What is mathematical operators? Later we will look at that. So the wave function is your complete description of a single particle in one dimension. So look at the one that I mentioned before, the psi. The psi, it has real. Ini saya bulatkan. And also it has imaginary part. Real yang ini, yang hijau, imaginary part yang biru dotted lines. Ini gambar dia. In a wave, the wave function contains imaginary and real. And the equation is like this. I don't think we should learn how to derive the psi. Because we will focus on the application of this formula. That is much, much better. Right? So what can we calculate? We could calculate the probability density, the most probable location of the electron to exist at certain places in materials. So we use absolute psi square. We have the equation of psi, so we use absolute psi square. And before that, we must use the normalization. What does it mean by normalization? Normalization is like this. Combination of all probability It could be 0, it could be 1. 1 is when the particle exists at that state, at certain location. Kenapa saya punya video ni ada lag Tak apalah, lag pun asalkan you masih dengar saya suara, that is okay lah. Okay. Right, so we carry on with the next slide. Oh, terlalu slow lah. We have a simulation over here. Let us try to understand waves better, because the wave function behaves like a wave. The psi is a wave function. It behaves like wave. So we need to understand wave even more. Look at this interactive simulation on the right side. Okay, kita ada simulation about the wave. Right, you have control sliders here. Dekat sebelah kiri tu, on your left hand side, you have control sliders on the amplitude, the wavelength, and also the frequency. Okay, so play with them. First, try to adjust the amplitude. See how the wave gets taller or shorter. Let's try to make it shorter. If we minimize the amplitude, the wave becomes shorter. If we increase the amplitude, the wave becomes taller. All right. That is the height of the oscillation. The height, the wave, the amplitude of the wave, the height. Right. So now change the wavelength or the lambda. Watch the wave compress or stretch. Let's try to adjust the wave. If we make the wavelength smaller, see, our wavelength now becomes compressed. If the wavelength, we adjust the wavelength becomes longer, we stretch our wavelength. Our waves become stretched. Okay. The wavelength is the distance between the peaks. You have the peaks, peaks, trough, peaks, trough. The distance between the peaks, that is wavelength. Or the distance between the trough, that is wavelength. If the wavelength is short, therefore, your distance between the peaks or the trough becomes smaller and smaller. So your wavelength is like a string, they become compressed. So if your wavelength is longer, it means the distance between the peaks or the trough becomes longer, and your string or your wave becomes stretched. This is logic, right? So notice how the wave number k automatically updates. Mana k? See over here, the wave number k. If we play around with the wavelength, see, the shorter the wavelength, the bigger the wave number, because the formula for wave number k is 2 pi over lambda. If lambda is bigger, therefore the k becomes smaller. See the difference, right? So the wavelength has connection with our wave number. Okay, phase velocity also have connection, because whenever we change the wavelength, the phase velocity also will be changed. How about the amplitude? Nothing changed in amplitude except the amplitude of the wave. The angular frequency, wave number, and period and phase velocity doesn't change with amplitude. So how about the next one? What's the next one? The frequency. Yes, frequency. Now try to adjust the frequency. The wave oscillates faster or slower in time. If we make the frequency smaller, we will change the angular frequency and also the period, because the formula for angular frequency is omega equals to 2 pi f. The higher the frequency, the higher the angular frequency. How about the period? Period is the 1 over frequency. It's the inverse of frequency. The higher the frequency, the smaller the period. See, the smaller the frequency, the higher the period. The higher the frequency, the smaller the period. It's inverse. The relationship is inverse. So remember the wave function, the formula is psi in terms of x coordinate and also the time. it's A sine kx minus omega t. So k is 2 pi over lambda over here. Okay, x is the position. Omega is the angular frequency. The relationship is 2 pi f. If the f is increased, omega will be increased. That's it. This is the wave function. These waves on your hand side was simulated based on the psi formula. Psi equals to A sine kx minus omega t. And we have three important parameters that we could play around that could be related to the wave function. So A, the lambda, and also the frequency. Okay, I need to text somebody first. All right. So what else? Let us see the sinusoidal wave derivation. So let me show you this wave equation. Let me show you where these wave equations come from. Step one, we write the general sinusoidal form, that is psi equals A times cosine kx minus omega t plus phi. Bukan psi, phi is phi. Phi is the phase. Huh? So sometimes we can use cosine, sometimes we could use sine. Both are correct. We can use cosine or sine in wave equation. See, the previous slide I used sine, but this slide I used cosine. Doesn't matter. Both are correct. Right? So the kx term gives spatial variation. Kx, this kx term, right? It gives spatial variation. Kx and x. X is a space. Yeah. Pada pasi x, kx. Different k, it will give us different x coordinate. The omega t term gives time evolution. Omega t. Dalam A cos kx minus omega t, kx is spatial evolution. Omega t gives time evolution, space and time continuum. And the phi, the last part of the equation, phi is an initial phase offset, meaning that the graph, that's the graph started from 0 degree or 90 degrees or 270 degrees or 360 degrees or any angle. So it is determined by the phi. Of course, cosine graph and sine graph is very it's very clear. Sine graph start from 0 degrees. Cosine graph start from 90 degrees. So there are variations, maybe 230 degrees or 45 degrees or any other angles. It was determined by the phi, the last part of the equation. Because graph won't start exactly at 0 or 90 degrees. They could start at any angle. Right? So step number two, from the condition that phase is constant for an observer moving with the wave. If then observer moving with the wave to the right or to the left, we take the differential and get that velocity equals to omega over k. Omega, dan yang macam W2 over k. So that's our phase velocity formula. The phase velocity formula is omega over k on your bottom right hand corner. Usually the equations will be given in the test or examinations. Right. So kx minus omega t plus psi is constant. Right. Step 3, we connect these two quantum mechanics using de Broglie relations. Step 3. Hey. Hold up. Yes, this one. Okay, using de Broglie relation. Momentum P equals to h bar times k, right? We have learned this before in chapter 1. And energy E equals to h bar times omega. These are the bridges between waves and particles. One equation tells us about waves. The other equation tells us about particles. The momentum part tells us about particles. And the other part tells us about the wave. So in combination, we are relating the wave and particle duality. So keep these relations in mind. We'll use them extensively when we derive Schrodinger equation shortly, right? So let us see the next slide. Quite slow. Actually, there is. You could play around with the animation. The time evolution. See how the evolution of time happened. How about if we change the phase constant? See, it's how the graph looks like. If we change the phase constant, the starting point of the graph, if the phase constant is 0, it's like this. Phase constant is increasing, it's like this. Remember, a wave function consists of imaginary and real part. The real part is the green one, and the imaginary part is the dotted purple line. So the cloud over there, if you could see, there is a cloud beside the two graph over here. This is the green one, this is the purple one. So this are the real and the imaginary part of the wave function. We have something like a cloud over here, the packet of cloud. So this cloud is actually the probability density. The psi is the combination of the green and also the purple graph. There's psi. They're the wave function of a particle. So if we want to calculate the probability density of the electron to exist at certain place, we must do the psi square, the absolute psi square. And if we plot using simulations or any mathematical modeling, we could say that the gray cloud is the probability density of the electron to exist. See, yang sini paling banyak kan kawasan dia kan. So most probably the electrons located at the center of the cross. Most probably, because the probability over here is very, very high. Yang kat tepi ni rendah sikit kan. Much lower at the both edges of the side. So this is how you imagine the psi square and the psi. The psi is sinusoidal form. Okay, usually the psi, the real part a bit backward, okay, and the imaginary part a little bit forward, depending on psi. Okay, kalau kita ubah psi, dia akan berubah-ubah lah. Psi pula, sorry, phi. If we change the phi, see, it will change the phase constant. Phase constant change, the graph will be changed. Ini simulation dan animation ni sebenar tau, bukan not artist representation. This is based on real simulation. That's why your slide now is a bit heavy, kan? Sebab ni based on real simulations. This is how the graph, the evolution of the graph based on different time. If the time is 20 seconds, see the graph moves to the right. Backward, this is time-dependent Schrodinger equation. This is the basic of time-dependent Schrodinger equation. Based on psi equals to psi equals to a sine kx minus omega t plus phi, we could get these three graphs. We get the real part, we get the imaginary part, and we could do calculations on the probability density. We get these electron clouds. So why do we need to calculate the electron clouds? Can we see these electron clouds using our naked eye? That's why we need the calculations. We need to predict where the electrons will be located. Because, for example, in the semiconductor industry, we only could feel the presence of the electron using multimeter, and there is no chance of us to see the electron. No way. We don't know the real face of the electron. We don't know. Only God knows. We don't know. You cannot see electron, but we could feel the process of electron using multimeter. But to use multimeter all the time is very, very hard. So usually we will use, scientists use simulations. For example, the density functional theory simulation. We have that simulation. Later, if we have time, we could use that simulation. Or wait until you take the BSP2452, the Advanced Material Laboratory, which you will have your hand on the FT simulations. Then you could see where the electron could be located at certain structure or certain atoms or molecules. We could predict that. Why do we want to predict that? It's like this. For example, the most important part is the semiconductor industries. Without knowing where the electron could probably be located, how can we extract the electron out? Because semiconductor is about partially conducting the electron to some other places. It's semiconductor. Electron is our currency in semiconductor. So in this real world, our currency may be in Malaysian ringgit, dollar, whatsoever. But in semiconductor, our currency is electron. Electrons is the currency in semiconductor. We need to move the electron. We need to liquidify the electron from certain place to other place to make the device work. So without knowing where the location of electron is, we don't know which part should it tap the electron. So this is the basic thing. The basic thing, knowing the electron. So this is the background of any simulation based on density functional theory. This is the background. The first thing happened inside your computer. They are calculating the psi square, the phi, and the electron density. This is what your computer is calculating. That's why your computer will be a little bit slow if you play around with this simulation, because your computer is calculating something background. It might be looks easy, but by sliding the slider, the phase, you change the phase constant, the time evolution, and you get a little bit annoyed if your simulation works very slow. But bear this in mind, by simple sliding, your computer is working very hard behind the scene, calculating something new every second, every time you change the slider. This is real simulation for you guys, right? So what else? Okay, now we need a powerful mathematical tool, which is Euler formula. Ada yang cakap Euler, it's Euler. Up to you, doesn't matter. This is how we spell it. Euler formula. Euler's formula. Look at the unit circle on the right. On your right hand side. Sini kan. You can play around with this angle. Slide the angle over here. For rotation speed. Kan, you could play with the rotation speed. If you click the see. The rotation speed kita slowkan lah. So it's moving, all right, it's moving. That is the rotating vector, okay, counterclockwise. And I want you to watch what happens. The angle is theta. The angle is in theta, the one with orange color, the angle is theta. As the theta increases counterclockwise, okay, the vector rotates counterclockwise around the circle. Very easy, you could observe that. Now look at the projections. The horizontal blue line shows cosine of theta. Ini classical physics pun dah belajar. The x component. Okay, the formula is cosine. See, on your x-axis, there is a straight line, horizontal straight line, always moving. When the particle is moving in circular motion, the blue line becomes longer and shorter and longer again to the right hand side and shorter again. So now it's moving to become shorter, moving to the right hand side, and then comes back to the left hand side. This is what happens when the particle is moving in circular motion. Okay, now there is another part. Okay, the vertical red line. This is the sine of theta. That's why in psi, inside we have sine A sine kx minus omega t, and we have A cosine kx minus omega t. What are they? They are the x and y coordinate. We can use sine, we can use cosine, or we can use both. So to combine the sine in the form of A sine kx blah 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 plus cosine kx, it's very, very tiring. It's very complicated to do that. So in short, we could use the Euler formula. Euler formula combines both cosine and sine form. Now here's the Euler's magic. So look at the Euler formula on your left hand side. So we have e to the I theta, e to the power of I theta equals to cos theta plus I times sine theta. What is I times sine theta? This is the imaginary part. Okay, the cosine theta is the real part. The I times sine theta is the imaginary part. So this exponential form is incredibly useful for quantum mechanics. Yeah, very useful. Why? Because the normal form of sine equals to A sine theta plus kx cosine, very, very complicated. But using the Euler form, it's very useful to make sure the equations much, much smaller. So we have dragged the theta slider just now and watch the relationship. Yeah, theta itu berubah. Yeah, let me try to stop first. See the angle? Whenever I change the angle, look at the cosine and sine form. Yeah. I want to change this angle. Look at the changes of cosine and sine form. Whenever the angle change, see the sine and cosine changes. Sometimes in the negative region, sometimes in the positive region, depending on your component of x and y. If the x component towards the left, then you will be, the cosine part will be negative. See over here. See, this one is, the blue one is in negative part. This is kinematics in classical physics. Kan? How about the y part? The y part is over here. Y, sebelah atas. So it's positive. So how about if we change downward over here? So our x still negative. Negative. Our y also negative. That's why we got negative, negative over here. Now this is classical. This, I think you could understand this easily. So what else? So we have tried to slide the theta, and we have the relationship. And when theta is 0, e to the I theta equals to 1. Macam tak tadi? When theta is 0. Okay, let us try one more time. Kan? Saya slide ke bawah ni. Di bawah ni ada lagi tau. You can slide. Nampak ni, I change the angle. See? Nampak ni. I change. Angle is 0. Look at the polar form. Ni, yang ni. Yang bawah ni. Kan? Yang bawah ni. Bukan. Mana tadi? Ni. Tengok yang bawah ni. Kan? Angle 0. Ni pun. E to the power I is 0. So your equation becomes 1. But kat sini 1. How about I sin theta? I sin theta is 0. So this is cos theta, you got 1. Yalah, cos 0. Cos 0, you got 1. This is a simple one. Right. So I sin theta. Theta is 0. Sin theta is 0. So I sin theta becomes 0. This is 0. See how it changes. So every time you move the angle, your Euler formula will be changed. Just use cos or sine only. That's it. No other complicated mathematical operation. Cos and sine only. I know that the look of the Euler formula quite intimidating, but it's actually cos and sine operation only. Use your scientific calculator. It's very easy. It's how it changes. So what else? So it's pure real, because the I part is 0. So your equation now is only real part. Now, at 90 degrees, if you change the theta becomes 90 degrees, let's say angle is 90 degrees, quite hard to change to 90 degrees lah. So if the angle is really at 90 degrees over here, I cannot change to exactly 90 degrees. This part, the real part actually will become 0. Because cos 90 degrees, you will get 0. It's minus 0. And your sine 90 degrees becomes 1. So your wave function becomes 100% imaginary. This is the calculation where, this graph is projected. This is how we calculate the imaginary part and also the real part. This is how we plot the green line, also the dotted purple line, based on the Euler formula. Okay, so the real part was calculated using cos formula. The green graph just now, you will look at just now, calculated from the cos formula. And the purple graph was calculated based on the sine formula, because I is imaginary. It's square root of -1. So instead of showing the square root of -1, which if you hit your calculation, you get error. So instead, we use I. This is the imaginary unit. As I mentioned before, in sine, in wave function, we have real part and imaginary part. And it is represented by the graph that I've shown to you just now. Based on different phi, you will get different graph. Okay. What else? Okay, we have clicked the play button just now and watched the automatic rotation. We have played just now. You could play around later in your own style. So this is how we represent oscillating wave function compactly. Instead of writing A cosine plus B sine, very time consuming, we write A times E to the power of I theta. It's in Euler form. So it makes calculus much easier. I know that we won't touch much about the calculus, but if you are in a calculus class, you will know how hard it is to derive or how to execute mathematical operation using the A cosine plus B sine. So Euler is much easier. Anyway, we won't touch that. Never mind. You have suffered enough in your calculus class, so we won't touch calculus much. So derivative of exponential are just exponentials again. Okay. So this is why quantum wave functions use the exponential form psi equals A times E to the power of I times kx minus omega t. Keep on playing this simulation until the connection between the rotation of the complex plane and the wave function feels intuitive. Play around with the simulation. Please play around with the simulation. It makes sense much better than you just read out loud the complex wave function. The complex wave function always looks intimidating, but after you look at the graph, it is actually very basic mathematics of cos and sine formula. If you have learned mathematics in your secondary school before, you can survive solid state physics. It's actually very simple. We don't derive the equation because the equations have been derived by Euler a few years back. He already passed away anyway. The Euler, what else? The De Broglie. They have suffered enough derive the equation, and you don't need to re-derive the equation. Just use the equation to apply in your solid state physics. Use the simple mathematics of cos and sine. That's it. Much easier. Okay, what else? The bond interpretation. Now we look at the bond interpretation simulation. So this is another one of the most important slides in the entire course. Bond. If you really still remember the story of Bond Oppenheimer, the movie of Oppenheimer, do not watch the movie. Contains lots of the science part, only half of it. The other part is you cannot watch this at home. Better to watch because of course Hollywood. You know Hollywood, they put science plus sex, drugs, and all that. Don't watch. Just read the story of Bond Oppenheimer. Two people, Max Bond and Oppenheimer. Bond is the teacher, I think. Max Born is the teacher, Oppenheimer is the student. Now look at the simulation on the right. On your right hand side, there is a simulation. I haven't played the simulation yet. You see two curves. You can see two curves. The blue dashed line, shows the wave function, the psi. The wave function psi. We haven't calculated the psi square yet. The probability density of electron to exist haven't been calculated yet. So this is the basic form, represented by the Euler formula. The Euler formula. So it can be positive or negative. We have trough, we have peaks, and we have trough repeated again in oscillatory movement. So crossing the x-axis, the graph is crossing the x-axis. Another part is negative, another part is positive. So the teal field area, it looks green for me. It looks green, but when I asked my wife, she said this is teal. I don't know. Okay, teal or green, the area under the graph. Okay. So the area under the graph, the teal or the green one, is the probability density. So when you do the psi square operation, you have psi, you do the psi square. So the teal field area is the probability density, which is always positive because psi square. Psi, you have negative and positive. When you do psi square, you always got only positive. So that is why the area in the graph only limited to the positive part of the graph. The probability density only appear on the positive side of the graph. Okay, in the upper part of the x coordinate. Sorry, the y code, the y equals to 0. So this is Max Born's interpretation from 1926. Yeah. So here's why it gets interactive. Choose different wave functions from the drop-down menu. We have the drop-down. I prepared from the drop-down menu. I think we have Gaussian wave packet. We have harmonic oscillator, n equals to 0, which is the ground state. We have harmonic oscillator, n equals to 1, which is the first excited state. N equals to 2, second excited state. Infinite well, superposition state. So choose the Gaussian wave packet first. Choose the basic one, Gaussian wave packet. For wave packet, the shape of the graph is bell shape, which is Gaussian wave packet. Gaussian type of graph. It's a bell shape, the basic one. Okay, choose the Gaussian wave packet and adjust the width sigma using the slider. The width, okay, this is the sigma. Adjust the slider. If the width is narrow, your graph will look like this. Width is very, very wide, so your graph will look like this. Okay, the width, this is very understandable, right? The smaller the width, your graph will become more compact. The longer the width, your graph will become loose or stretch. Very easy, like this. What else? And watch how the wave spreads out or localized. This is what we call localizers. Now click the sample particle button. Sample particle button. See? Kurangkan. Oh, jadi slow lah. The simulation has become quite slow because lots of simulation is going on at the background right now. So if you point your cursor at any places of the simulation, it gives you the value. For example, you look at the middle line, the psi square is about half. It means the probability of the electron to exist over there is 50%. Look at the graph. It shows psi square about half, 0.47. It's about 50%. Okay? Over here, the chi-square is 50%. How about over here? See, the chi-square is about 0.14%. It's about 14%. Much lower probability of the electron to exist at the edges of the Gaussian graph. This is based on real calculations from the Euler formula just now. You don't worry, you don't need to calculate this manually, because to calculate this, you need, I think, more than 30 pages. I don't want to, to have hundreds of pages of test scripts for each one of you. I don't want that. Never mind, you don't have to calculate. This could be calculated by the computer, not by you. So what else? So we have adjusted the sigma, and now click, okay, we have clicked the sample particle. The sample particle and the green, the orange dot lines, those are the probability that electrons could exist. The particle could exist over there. What else? So you see the dots, the yellow or the orange dots appear randomly, but they cluster. They appear random. Yeah. But somehow they cluster where chi-square is large. And they will form this Gaussian type of graph as well. They will fill the gaps in the Gaussian type of graph. So click it 10 more times. Try to sample particle. Click it 10 times. Oh, it's quite. Oh, I clicked the wrong button. Click it many times. See, the particle become more and more, filling the area under the graphs. So we clear again. First click, second click, third click, fourth click. See, the probability, the particle become much denser and denser and denser. See, the movement of the graph. This is how it moves. See. Right. Don't forget to look at the X, delta X probability, maximum probability about 0.47, 47%, about 50% of the probability of the electron to exist over here. You can change to some other graph as well. Can change, but bear in mind that we haven't learned the harmonic oscillator yet, N1, N0, N2, infinite. Well, we haven't learned yet. Up to this lecture, we only learned the Gaussian wave packet first. The probability of electron to exist at certain place in the structure of molecules or structure of atoms. Okay. Harmonic oscillator, N0, 1, 2, and so on and so forth, we haven't learned yet. Okay. Nanti kita akan belajar. Not yet. So what else? Okay, we have clicked the start time evolution. Okay, I click the start time evolution, the sample particle over here. Okay, yep, the sample. Okay. Watch the wave function evolve. For a Gaussian packet, the probability moves. It's not stationary. For harmonic oscillator eigenstate, the probability stays fixed even though psi rotates in the complex plane if you change. Sample particle. Tak apa, yang ini kita akan, we will learn this later in the next topic nanti. Right. So what else? Oh yeah, normalization. Normalization. I think normalization will be covered tomorrow. Tomorrow we will have class. Tomorrow. I'll make another video about the normalization. Why do we need normalization? But I don't think you need to show the derivation of normalization. I don't think we need to do that. Okay, because we are material technologists, we are not actually particle physicists. But the function behind the calculations is always like this. I don't think we need to derive this, because previous semester, the direction of the course is quite different. Students need to derive this subatomic particles equation, but I don't think we need to do that. We are technologists. we need to apply these equations to simulate something that is much, much better, much more aligned with your course. So I think that is all for today. We'll continue our lesson tomorrow. We will have class tomorrow, face to face. So thank you for watching. Class dismissed.